Let's talk about the invisible forces that are, well, all around us, shaping our entire world. From the music coming through your headphones to the light from this very screen, it's all governed by one simple thing: waves. So we're going to break down what they are and exactly how they work.
So, riddle me this. What does a vibrating guitar string, a stadium packed with fans doing the wave, and the ground literally shaking in an earthquake all have in common? They seem totally unrelated, right? But believe it or not, you're all connected by one single fundamental idea. They are all waves, and their main job is to move energy from one place to another.
So, here's our game plan. First, we'll start with the absolute basics, what a wave even is. Then, we'll dive into the two main types, learn the lingo to describe them, check out how they behave out in the real world, and finally, see how we can actually measure them.
All right, Section 1. What is a wave? Before we get into all the different kinds and how we measure them, we've got to nail down this core concept of energy in motion.
Okay, this right here is the single most important definition we're going to cover today. A wave is a vibration, an oscillation that transfers energy, not matter. Think about a ripple in a pond. The energy of the ripple moves across the water, but the water molecules themselves, they just kind of bob up and down in place. They don't actually travel with the wave. It's all about transferring influence, not transferring stuff.
Okay, so now we know what a wave does. But it turns out there are two main ways they get the job done, and it all boils down to the direction of that vibration. We're talking longitudinal versus transverse waves.
And, the difference is super clear when you picture it. On one side, you've got longitudinal waves. Here, the vibration is parallel to the direction the energy is going. The classic example is pushing a slinky. That little bunch up, that compression, travels right along its length. But on the other side, you have transverse waves. For these, the vibration is at a right angle, perpendicular, to the direction of the energy. Just imagine shaking a rope up and down. The rope itself moves vertically, right? But the wave travels horizontally, away from you.
So let's zoom in on those longitudinal, or push waves. You find them all over the place. Sound waves, ultrasound, even the P waves in an earthquake. And here's a fantastic little trick to remember this one. A seismic P wave is all about pressure, it pushes, and the particles move parallel. How great is that?
And on the flip side, we have the transverse or shake waves. This category is huge. It includes everything from ripples on water to all forms of light, the vibration of a guitar string, and the other kind of earthquake wave, the S wave. And you guessed it, there's a mnemonic for this one too. Seismic S waves shake the ground from side to side. Easy peasy.
Okay, to really dig into waves, we've got to learn to speak their language. So this next bit is going to be a quick fire round of the key terms you absolutely need to know to describe any wave you might run into.
First up is amplitude. Put simply, this is just the wave's intensity or power. It's how far a point on the wave moves from its normal resting position, so how high the peak is, or how low the trough goes. A bigger amplitude means more energy. So a really loud sound is just a sound wave with a high amplitude, and a super bright light is a light wave with a high amplitude.
Next, we've got wavelength, which scientists represent with that Greek letter lambda. And it is exactly what it sounds like. It's the physical length of one complete wave. The easiest way to picture it is the distance from the top of one peak to the top of the very next one.
And then there's frequency. This one is all about timing. It's how many complete waves pass by a single point every single second. We measure it in hertz. And this is a really big deal. For sound, a higher frequency means a higher pitch. For light, a higher frequency actually changes the color we see.
Now here's the magic. This is where it all comes together. Those three things we just talked about, speed, frequency, and wavelength, they're all linked in this beautiful, simple equation. The speed of any wave is just its frequency multiplied by its wavelength. This little formula is one of the absolute cornerstones of physics.
All right, so we know how to describe a single wave. But waves don't just exist in a vacuum. Well, okay, some do. But most of them are traveling through stuff. So what happens when a wave crosses from one material or medium into another? Let's talk about crossing boundaries.
This phenomenon has a name. It's called refraction. It's just the change in a wave's direction when it hits a new medium and its speed changes. And I guarantee you've seen this a million times. You know how a straw in a glass of water looks like it's bent? That's refraction. As the light wave goes from the air into the water, it slows down, and that causes it to bend. But it's not just for light. Any wave can be refracted.
And wow, the medium can have a massive effect on a wave's speed. Just look at sound.
In the air, it's zipping along at about 330 meters per second. But move it into water, and that speed jumps to 1,500. And in solid steel, an incredible 6,000 meters per second. It's all because the particles in a solid are packed super tight, so they can pass that vibration along way more efficiently. This is also why you can't hear sound in space. A vacuum has no particles to carry the vibration at all.
Okay, so this all sounds great in theory, but how do scientists actually go about measuring this stuff in the real world? Let's look at a couple of classic experiments that put all this theory to the test.
Here is a brilliantly simple way to measure the speed of sound. You have someone stand a very specific distance away, let's say 400 meters, from a starting pistol. When the gun is fired, you get a visual cue, like a puff of smoke. The observer starts their stopwatch the instant they see the smoke, and they stop it the instant they hear the bang. After that, it's just grade school math. Speed equals the distance you measured divided by the time on your stopwatch.
So, if we run the numbers from the example, a 400-meter distance and a time delay of 1.2 seconds gives you a speed of 333 meters per second. Now think about that. The scientifically accepted value is around 330. That is shockingly close. The tiny difference is probably just a little bit of human error with the stopwatch. It's an amazingly accurate result for such a simple setup.
So what about water waves? Well, for those, labs often use something called a ripple tank. They use a motor to make these perfect, steady waves. From there, it's pretty straightforward. They can measure the wavelength just by looking, the distance from one peak to the next. Then they can figure out the frequency by counting how many waves pass a certain point in, say, 10 seconds. And once you have frequency and wavelength, you just plug them right into our big wave equation to find the speed. Look, if you only remember one single thing from this entire explainer, please make it this. This is the golden rule. All waves transfer energy, but they do not transfer matter. They are movers of influence, not movers of stuff.
And honestly, with that, you've totally got the fundamentals down. You now know the difference between push waves and shake waves. You can speak the language of amplitude, wavelength, and frequency, and you know the key equation that connects them all. That is a seriously powerful foundation for understanding a huge part of the world around us.
So, I'll leave you with this last little thought to chew on. We've established this incredible principle. Waves transfer energy without moving matter. But where else in the universe does that idea apply? From the tiniest quantum particles to the scale of entire galaxies, where else do we see influence being transferred without any actual substance moving along with it? Thanks for diving in with us today.